let me remind you that last time we talked about sensitivity analysis, and recall that it was about the following. We started with some problem. Some problem given by a table. We have something like this. Vector running inside V, vector of coefficient C, some columns. Then we solve this problem. And we got some answer, some table where some variables are basic. To go from here to here, we can do the following. We can take the columns of the basic variables, denote them, the results will make it of B. And then here we have vector of right hand side, which is B inverse B. These numbers, well, how the matrix gets transformed. If this is n some column for coefficients of variable xi, and this is some number cxi, then what will happen here, we have B inverse n, and this number will be cxi minus the row of basic coefficients here times B inverse times nxi. And here we have z, here we have z minus something. So, first of all, we do have a way to go from the original formulation of the problem to the final table if we know basically one thing, the set of basic variables in the final solution. Well, to find the set of basic variables in the final solution, we typically have to actually perform a simple algebra. It's not that simple. However, in some cases, when you don't want to solve the problem from scratch, if you already solved a similar problem, then you sometimes do know some basis which is either exactly the optimal basis or not too far from it. So maybe it gives you a feasible solution, but not quite optimal, you have to re-optimize it. And that's what we did last time. We started with a problem like this, and then we made some changes. Let's say a change in one column. So you replace n by some other vector, n prime and tilde. You replace this coefficient by some other number, and you see what happens to the final table. And last time we discussed if the change is restricted to just one column like this, especially if it's non-basic, then it propagates to this table as change only in these numbers, in this one column. So it always stays feasible, the solution always stays feasible, but it could be not optimal. And we discussed, well, if it is not optimal, if this number becomes positive instead of negative, then we can perform the simplex algebra. So I just summarized in short what we did last time. We also discussed what happens if this change was in a column corresponding to a basic variable, and that was a little bit harder. We decided that the update would be as follows. First we'll update it as if it was a non-basic variable, then it will create a problem for us, because well, it will actually become non-basic. Then we'll have to perform one pivot to make it basic, and once we perform this pivot, well, the solution could become not feasible, these numbers would become negative, and also not optimal. And I promise that today we'll discuss what to do in these cases. Well, before we go there, I want to discuss a simple change. What happens if you change this column? Just one column, but the column of right hand side. And this change is actually, well, it's something that in real life people do worry about this change. This vector of right hand side, typically the problem is about how many resources, what is the amount of resources that you allocate to this particular production, this particular factory. And these amounts are usually, well, they are not independent of the overall plan of overall strategy of the company. So if the company wants to optimize the production in one particular factory, well, it can divert resources from another factory which it also controls. So sometimes people do want to understand what happens when you make small or large changes to these vectors on the right-hand side. What's good, we already discussed what happens when you do small changes to the right-hand side. If you recall, well, if you allow yourself some extra resources to understand what happens to the optimal solution, well, all you have to do is value the resources. How much the resources are costly at fair prices, and the fair prices are the shadow prices. So, if you want to make just a small update to the right-hand side, you don't have to do, well, anything. You just have to figure out what are the shadow prices, which are basically written for you here, and, well, use it to understand what will be the change in the optimal solution. However, if the change is large, well, let's see what will happen. So let's discuss change in B. Example B. So the change will propagate, will only to the vector of right-hand side. Indeed, if you change just this one vector B, well, the vector of coefficients CV doesn't change. The basis matrix does not change. This whole thing, all the columns don't change. So the final row doesn't change. The matrix itself doesn't change. Every row, every column, well, it used to be n, it's still n. The only change, well, basically there are two changes. One change is the change in this thing, B inverse B, now it will be B inverse B tilde. And also the value of the actual function might also change, but well, that's maybe not that important. You want to understand what is the solution. Once you have the solution, it's very easy to find the value of the optimal function, of the objective function. Okay, so it will change. Instead of B inverse B, it will be B inverse B tilde. Alright, so if B inverse B tilde is still positive, so if all the entries are still positive, then we have no problem. Then the solution is optimal. Is feasible and in fact optimal. So being feasible means exactly that the right-hand sides are positive. Just recall that the vector of right-hand sides does give you the value of the decision variables. Sorry, of the basic variables in this final table. The basic variables, near them the coefficients suggest the identity matrix. So once you plug in all the non-basic variables equal to 0, you get that the basic variables are equal to the corresponding right-hand sides. So this vector is basically the vector of solutions for the basic variables. If it is positive, then we do get a feasible solution, which is of course optimal. The last row used to have negative numbers, and still it is the same row. Well, what happens if the inverse B tilde is not positive? Well, then the solution is unfortunately not feasible. So you do get values of some basic variables. Well, they're negative. If this vector is not positive, it means it has some negative entries. The basic variable corresponding to this entry should be negative. That's not good. You don't want negative answers. However, this solution, well, it does look somewhat good, but optimal. In what sense? Well, in the sense that you can't increase any one of the variables to make the objective function even larger. Well, it's not feasible, some of the variables are negative, but still the last row in the tableau consists of negative numbers, so something is good about this thing. Maybe there is a way to use this somehow. Well, if we get not feasible solution, we kind of don't know where to start the simplex algorithm. We always have to start it with a feasible solution. Well, so this situation kind of not familiar. But think now about, well, okay, so think about the dual problem. So somehow we realized in the first place that small changes in the right-hand side are actually related to the shadow crisis to somehow to the dual problem. So maybe here thinking about the dual problem will also help us. So think for a second about the dual problem. So let's make some digression on duality. I just want to remind you how duality works. How given the primal problem you can find the dual problem, and well, then I'll be able to point out how it will help in this situation. So if the primal problem is something like this, sum of aij xj is at most bi, and you want to maximize z, which is sum of cj xj, then the dual, well, now you take, here you take sums in rows, now you take sums in columns. Sum of aij yi. You want the sum of column to be larger than the coefficient here, at least cj, and you want your objective function is now the corresponding linear combination of the right-hand sides. Sum of bi yi. And here you want to maximize this thing, here you want to minimize this thing. So I just reminded you how the work works. Maybe let me rewrite it in standard form. I don't want such signs, so I'll take minus sum of aij yi at most minus cj, and I want to maximize minus this thing. Not give the name of w to this, let me call this w. So that's how duality works. Let me show how the corresponding table changes. So in table form, it looks like this. In the primal problem, we have some matrix of coefficients times x is equal to b, and I want to maximize z, which is c times x. That's the primal problem. The dual problem is about, now I want to multiply the columns of A by some vector. So to convert the rows of A to columns of new matrix, I'll take the transpose. Transpose, if you recall, is just take the matrix and reflect it in the diagonal. So instead of Aij, write Aji. So A transpose times the vector of, well, the dual decision variables with the minus sign is at most minus c, and I want to maximize W, which is minus B transpose times y. So this used to be a column, now I convert it to a row and multiply it by the column vector y. And of course, I want to keep everything positive. So just rewrote exactly the same equations in matrix form. But now look something funny happens. What used to be the vector of right-hand sides in the primal, you see it, well, becomes minus the vector of coefficients in the dual. And vice versa, the vector of coefficients in the vector of right-hand sides in the dual is the vector of coefficients in the primal, with a minus sign. So now think about this situation. Here we are changing the vector of right-hand sides. And unfortunately, we get a non-feasible solution in the end. Well, but what will happen to the dual problem? What used to be the vector of right-hand sides now will become the vector of coefficients. So now we will update, in the dual problem, we'll update only the vector of coefficients. So the solution of the dual problem does not change. The shadow prices, well, there used to be some shadow prices, they used to be positive, they are still positive. We still get a feasible solution for the dual. Unfortunately, it's not optimal. Well, what to do? We know what to do. Do several steps of the simplex algorithm, but for the dual, not for the primal. So here we have a solution which is not feasible but optimal. In the dual problem, we get a solution which is feasible but not optimal. So we do have this duality between primal feasible and dual optimal, and primal optimal and dual feasible. Okay, so our basic idea would be, instead of performing the simplex algorithm on the primal problem after this update, perform it on the dual problem. Unfortunately, it's not the best possible idea. I mean, it is a good idea, but not the best possible. If you perform simplex algorithm on the dual problem, you'll get, well, the dual solution. You'll get, as your answer, the dual prices to the optimal solution in the primal problem. Well, I actually wanted not the dual prices, not the shadow prices, I wanted the actual solution. So we'll do something even better. We'll make updates in the simplex algorithm right here, which correspond to the updates in the dual problem. So we'll choose the entering variables and leaving variables as if we are doing the simplex algorithm of the dual problem. But the beautiful trick will be, we'll actually perform the updates, the pivots, on the primal problem. So let me write down this idea, and then I'll make it both more precise and hopefully understandable by showing an example. So, first of all, idea. Change in right-hand sides in primal is the same as change in vector of coefficients of the objective function in the dual. So in the dual problem, we get a feasible solution. Which might not be optimal. Simplex algorithm will pre-optimize. Well, now I will try to make the simplex algorithm on the dual problem with updates on the primal problem. So I'll decide which variable will leave the basis and enter the basis for the dual problem, and then I will know what will be the corresponding change in basis for the primal problem. Because recall, the basic variable in the primal are the non-basic variables in the dual. And the basic variables in the dual, well, they are not, sorry, the basic variables to the primal correspond to the non-basic variables in the dual, and vice versa. So if I know which variable leaves and enters the basis in the dual problem, I know which variable should leave and enter the basis in the primal problem. Except that whatever variable enters the basis in the dual problem will leave the basis in the primal, just because we have this funny duality happening. The basic variables in the primal correspond to non-basic variables in the dual. So we will use the what's called dual simplex algorithm for the primal problem. So conceptually, the dual simplex algorithm is as follows. Given the primal problem, you formulate the dual problem, you look what is the entering variable and what is the leaving variable for the dual problem, and then you don't make the update on the dual problem, you go back to the primal problem. Once you know what variable enters and leaves the basis for the dual, you know what happens in the primal, which one enters and leaves the basis, and you make the update in the primal. Next step, once again, we have a new primal problem, formulate its dual, see which variable enters and leaves the basis, update the primal. So it's exactly the usual simplex algorithm with the following pivoting rule. So first of all, in the dual problem, the variable which will enter the basis should be the variable with the largest coefficient in the last row. Well, so it should be the variable yi with the largest value of minus vi. Okay. Now, the shadow prices, the decision variables for the dual, or the basic variables for the dual, correspond to non-basic variables in the primal. So the variable which enters the basis, enters the dual basis, leaves the primal basis. So leaving variable is xi with largest with kind of most negative bi, coefficient bi. So we go and look in the vector of coefficients bi. We look for the number such that minus bi will be the largest positive number. So in fact we are looking for the most negative coefficient bi. Okay. There is a, well, small problem. What happens if there are non-negative coefficients? If all the coefficients are positive? That's actually a simple question. So, if all the numbers bi are positive and all the numbers ci are negative, then we are done. The solution is, well, it is optimal because the cj's are negative, and it is feasible because all the bi's are positive. So here we have kind of a condition for stopping. So if all bi are positive, we are done. Okay, what about the entering variable? Fortunately, I can't leave this board, and I can leave it, then it falls down once again. So I'll continue probably over there. So, entering variable well, it should be the variable which leaves the dual basis. The variable which enters the primal basis is the corresponding variable which leaves the dual basis. Well, how do we decide which variable leaves the dual basis? We look at the column of the new basic variable in the dual problem. In this column, we look at the quotients. Cj divided by Aij over there. And among these quotients, we find the smallest one. Whichever the smallest quotients, this is the, well, the pivot row or the leading variable for the dual problem. So it will be the variable xj with the smallest cj over a, sorry, ci. I want the, so I call the leading variable xi. So I want to go over, yes, over Aij and Cj. With the smallest positive quotient like this. So I'll go over the column in the dual problem, Aij's, I'll go over the column of coefficients in the row, which is Cj. I'll take quotient of each two entries, Cj over Aij. I'll only go over the positive quotients. I don't care about the negative ones. They don't give me a constraint how much you can increase the variable, the dual variables. And, well, I find the smallest positive quotient. This will be my new entering variable. And once again, the question arises, what happens if there are no positive quotients? What happens if they are all negative? That's a little harder question than the previous one. Let's think about it. If we are trying to decide which variable will enter the dual basis, we find out, so we try to, the thinking goes like this. We try to increase the basic variable until some constraint, well, gets actually hit. Until the inequality becomes actual equality in one of the constraints. Well, if all the quotients are negative, it means we can increase the dual variable as much as we want. So this will mean that the dual problem is unbounded. So what happens to the primary problem? Infeasible. Yes, exactly. So if all Cj over Aij are smaller or equal than 0, the problem is infeasible. So the dual is unbounded, hence the primal is infeasible. Well, and that's it. So once we thought hard about the primal problem, the dual problem, we can basically forget about the motivation. Now we have a set of quite mechanical rules. Each time you want to update the primal problem, which is dual feasible, which means kind of sort of optimal, which means the last row in the dictionary consists only of negative numbers. So once you want to update, to perform the simplex algorithm in such a problem, well, you will not employ the usual simplex algorithm, because you might not have a feasible solution to start with. But you can employ this algorithm. You will update the basis according to the following rules. The leading variable will be the one with the largest coefficient on the right, with the most negative coefficient on the right hand side. The entering variable, the one with the smallest positive quotient. Okay, so let's consider an example. To see how all this actually works in practice. So let's say that the original tableau is 2, 3, 5, 1, 0, 9, 1, 2, 3, 0, 1, 5, and Z is 3, 4, 8, 0, 0. X1, X2, X3, X4, X5. And the final table is 1 minus 1, 0, 3, minus 5, 2. 0, 1, 1 minus 1, 2, 1. 0 minus 1, 0 minus 1 minus 1. 0 minus 2. And the question is, find, so this is a solved linear optimization problem. This was the original formulation. This is the final answer, final table. The question is, suppose now you understand that this 9 will change to a 5. What will happen to the optimal solution? So find the solution, go to the solution. B gets changed into which is 5 pi. So instead of 9 pi, now it is 5 pi. Well, let's see. Our basis, what variables are basic in the original problem, the solution of the original problem? So you should be looking for variables which have columns which consist only of zeros and ones. Basically zeros and 1, 1 at one place. What are these variables? x1 and x3. Correct. So basis consists of x1, x3. The fact that it's in ordered basis, I always start with looking for a column with 1, 0, 0. That's my first variable. Next one will be 0, 1, 0. So here that's it. There are only two constraints. If I have more, well, I'll find 0, 0, 1, 0, and so on and so on. Okay, so this is my basic. Basis, what is my inverse of the basis matrix? The basis matrix is 2, 1, 5, 3. Its inverse is also written somewhere here. So we discussed where to find the inverse. The last two columns, right. So if we update from here to here by multiplying the matrix by the inverse, then this identity matrix will get updated to the actual B inverse. So this is 3 minus 5 minus 1, 2. Well, new right-hand sides. It will become B inverse B tilde. We know that nothing else will change, only this. And it will be 3 minus 5 minus 1, 2. Well, we'll have to actually compute this. Times, instead of 9 pi, we'll have 5 pi. So we'll get 15 minus 25 minus 10 minus 5 plus 10, 5. So, new kind of final tableau, I'm writing final in quotation marks because it's not final. It's what corresponds to the final tableau in the original solution, but now it might not be feasible solution. In fact, it will not be feasible because of this minus 10. So, the whole tableau is exactly what it used to be, 1, 0, 0, minus 1, 1, minus 1, 0, 1, 0, 3 minus 1, minus 1, minus 5, 2, minus 1, except for this one column. So in the right hand side I'll have minus 10 pi, and I'll get 10 minus perhaps some new value of objective function. Maybe let's compute this objective function. How do I find what is the value of objective function here?
Can we just say negative 1 minus the old one? We can use the old one, right?
Or we want to update from here to here?
Use
We could do this. There is slightly more straightforward way. Just the solution here. The solution here involves, well, x1 and x3. x1 is minus 10 and x3 is 5. And the objective function, well, it's still the same. 3x1 plus 4x2 plus 8x3. So the objective function is 3 times minus 10 plus 8 times 5, so minus 30 plus 40 minus 10. So this 10 comes as 3 times minus 10 plus 4 times 0 plus 8 times 5. To be honest, I didn't have to compute this objective function. I mean, it's not important what it actually is, but it will be useful for me to make some point data. So I'll compute it later. Okay, so here I have a new table. Unfortunately, it's not the kind of table that we are used to when performing the simplex algorithm. The vector of right-hand sides is not positive. I mean, if it were positive, it would be the actual final answer, a feasible solution, which is also positive. Unfortunately, it's not feasible. So we'll try to repair this. We'll try to keep the solution optimal at all times, which means dual feasible at all times. I'll try to keep these numbers negative, and I'll try to make these numbers actually positive by performing this dual simplex algorithm. So let's see. The variable which will first give the basis will be the variable with the most negative right-hand side. So let's go here. I'll mark the variable which will give the basis. It is the variable with the most negative right-hand side, minus 10. So this will be my pivot row. Pivot row corresponds to the variable which gives the basis. So the pivot row is the one with the most negative number on the right. Very simple. So this is the most negative. Pivot column. I want to find the variable which corresponds to the smallest positive quotient, Cj over Aij. Okay? Also shouldn't be very hard. So, 1 over 5, right? Yes. So once I decided that this is my, well, this is Ai, I mean Aij will be from this row. I'll look at the following quotients. 0 over 1. I don't want it. It's not positive. So I can write down my positive quotients. 0 over 1 is not interesting. Minus 1 over minus 1 is interesting. So here I have 1. 0 over 0, well, not interesting. Not identified. Not interesting. Minus 1 over 3. Not interesting, it's negative. Minus 1 over minus 5, interesting. 1/5. In fact, it is the smallest positive quotient. So this will be my pivot column. This will be my entry variable. Smallest positive quotient. And now I'll make an update. So I'll use this entry as a pivot entry, this pivot column, this pivot row. Update. So we'll divide the first row by minus 5. 0, minus 0, 5, 1, 2. Very good. This number is now positive. That's something very good. I'll update this number, so this second row, so it will be the second row plus 2/5 of the first row, so it will be 2 over 5. 1 minus 2 over 5 is 3 over 5. 1 minus 1 plus 6 over 5, 1 over 5. 0. 5 minus 5 plus this times 2 fifths. So 10 over 5 is 2 times 2, so it is 1. 5 minus 4. And finally, the row of coefficients. I want to make sure that these coefficients are still all negative. So it will be this row minus the first row times 1 over 5. So it's minus 1 over 5. Minus 4 over 5. 0. Minus 1. Minus 3 over 5. So minus 8 over 5. Minus 1. 0. Z minus, well, let's see, minus 10 and minus 10 over 5, so it is plus 2, so minus 10. So just perform the pivot, this pivot. And now magically I can get a solution which is both feasible, 2 and 1, and optimal. This vector is a vector of negative numbers. Which variables do I have? X3 and x5 are now basic variables. So solution x3 is equal to 1, x5 is equal to all others are 0. So that's how it will always work. Once you update the vector of right hand sides, you will get a table which is dual feasible, which means kind of optimal. Unfortunately, the actual solution is not feasible itself. So it's dual feasible, but not primal feasible. The shadow prices are all positive, these coefficients are all negative, but the actual numbers, the actual decision variables are not positive. Once we encounter this situation, we'll perform several iterations of this dual simplex algorithm. So the pivot row is always a row with the most negative number on the right hand side. The pivot column corresponds to the smallest positive quotient. And then you make the update. When you make this update, you should, how will you find sort of mistakes in your dual simplex algorithm? In the dual simplex algorithm, the solution always stays dual feasible, which means these coefficients, if you perform everything correctly, if you make all the arithmetics and all the choices correctly, these numbers must always stay negative. If you encounter at some step a positive number here, you know that you made a mistake. Dual simplex algorithm works as follows. It starts with a dual feasible solution, and it always keeps it dual feasible. The value of the objective function is not going to increase. That's not what you are trying to do. It will always decrease. It will keep decreasing at each step. What is the reason for this? Well, we started with a solution which is kind of optimal, cannot be increased, but it was not feasible. What you'll try to do is make it more feasible at the price of, well, making it a little smaller, making the objective function a little smaller. But the solution will become eventually feasible. Okay, so maybe any questions about this dual simplex algorithm. So we'll have a chance to discuss one more example before I go to kind of new ideas, maybe any questions about this one. This one is the simplest one, is one iteration, but it has all the features. There are data of these numbers, there are data of right-hand sides, there are data of objective function. Okay. So let's now discuss one more kind of change. Which is also very useful in practice. So we discussed what happens if you change one of the columns. In fact, we discussed all possible columns. Non-basic variables, basic variables, right-hand side. We even discussed what happens when you add one more column. So what happens if you kind of add a production line. Now we'll discuss what will happen if you add a new constraint. Sometimes it happens that you realize that implicitly you had to satisfy some constraint, but somehow you forget to tell somebody about it. So this somebody solved the problem, but now you tell him, well, you know what, now I recall, actually x3 plus x4 should have been smaller than 5. Well, you know what, your solution is no good. Well, once again, we have a strategy how to solve the new updated problem without performing the simplex algorithm from scratch. So what happens? So adding a new constraint. That's a new method. And let's discuss an example, and then we'll summarize what happens in general. So find the optimal solution. If the constraint x1 plus x2 plus x3 is at most to this problem. So I'm still discussing this problem. This was the original problem. We found that the solution to the original problem was 2, 0, 1. But now somebody comes and tells you, you know what, your solution is no good. I actually wanted the solution to satisfy 2x1 plus x2 plus x3 that moves 2. So our original solution which was x1 equal to 2, x2 equal to 0, x3 equal to 1, does not satisfy the constraint. That's always something that you want to check. So maybe the management comes to you and tells you, you know what, I recall that I have another 100 constraints. If it happens that your optimal solution already satisfies these 100 constraints, then you don't have to repeat anything. You already found a solution which is the optimal solution. Well, yes, it does satisfy some other constraints on resources, so it's still optimal. The problem is with these cases, when the new constraint is actually binding, when the new constraint is actually restricting you from using your previous found optimal solution. Well, if it is actual new constraint, let's add it, but not to the very first step of the simplex algorithm. That would be repeating all the work that we already have done to find this. Let's add it to the very last step. So the idea is now add it to the final table. So take my final table where my constraints are written in this way. 0, 1, 1, minus 1, 2, 1. And I will add this one new constraint. 2, 1, 1 is at most 2. I know that for this new constraint I'll have to introduce a new slack variable, so I will add one extra column here with 0 coefficients for the other constraints, but coefficient 1 for this new constraint. And still my function will be z minus 14, 0, minus 1, 0, minus 1, minus 1, 0. So this row is a new row. And actually this column is also a new column. So once again, this row stands for the new constraint, this column stands for the new slack variable which corresponds to this constraint. Well, there is a problem with this new table. It's not even a table of a basic solution. What is the basis here? Where is the vector of 1, 0, 0, 0? Nowhere. Well, my previous basis used to be x1, x3. But now, unfortunately, I do have these numbers which are not zeros. Of course, they are not zeros. This new constraint which the management told me doesn't know what my basis is. It's just some actual constraint. And also, first step, I'll make it basic. So first, I want to make these numbers into zeros. So I'll kind of do a pivot on these two entries. I'll use these two rows to make these numbers into zeros. So I have to subtract 2 times the first row and 1 times the second row. So my first step is doing this thing. Updating my constraint so that it is actually in basic form, so that it respects what my basis is. So my rows, first 2 rows are unchanged. Minus 5, 0, 2. 0, 1, 1, minus 5, 2, 0, 1. Third row will be changed. It will be what it used to be, minus 2 times the first one, minus 1 times the second one. So 0, 0 here. Here it will be 1, minus 2 times minus 1. So this will be 3. And minus 1. So 2. Here it will be 0, minus 2 times 3, and minus 1, minus 5. 0, minus 2 times minus 5, 10, minus 2, 8, 1, and 2, minus 2 times minus, minus 2 times 2, and minus 1. So 2 minus 4, and minus 1, minus 8. The last row will be still good. Z minus 14 is still 0, minus 1, 0, minus 1, minus 1, 0. Okay, now I do have the basic solution. The variables which are basic are this one, 1, 0, 0, 0, 1, 0. And miraculously, there is one more. Well, of course, there is one more. We added in the very first step a column of 0, 0, 1 for the slack variable. So 5, 6, 4, 5, 6. So now we do have a basic solution. It is still optimal because I didn't do any changes to the last row. Unfortunately, it might not be feasible. You see, in fact, it must be not feasible. Why do I say it must be not feasible? Well, this minus 3 is the slack variable right here. It's a slack in the constraint which I added. Well, but my constraint was not satisfied. If it actually had a positive slack, it would be satisfied. But no, it is not satisfied, so this number must have been actually negative. So after this update, I will always get a solution which is optimal. The correct technical word is dual feasible. So these numbers are all negative, but not feasible. But now I do know what to do. I will employ the dual simplex algorithm. If I have a solution which is optimal but not feasible, dual simplex algorithm will work. So let's see how it works. Dual simplex algorithm. I'll choose the leading variable, the pivot row. It will correspond to the most negative number on the right hand side. I only have one. So this is my pivot row. What about pivot column? Should be the smallest positive quotient among these quotients. So find the positive quotients. Zero, not interesting. Minus 1 over 2, not interesting. 0, minus 1 over minus 5 is interesting. Minus 1 over 8 and 0 over 1, not interesting. So I only have one positive quotient. I'll have to make this the pivot column and perform the pivot. So let's be a little bit smart about how we perform this pivot. I know that these numbers will be all negative. That's how the dual simplex algorithm works. Basically, the choice of this column is the pivot column will guarantee that these new numbers will be negative. The right hand sides, well, it could be positive or negative. So I'll have to compute the right hand sides. If I get positive numbers, I know I'm done. If I get some numbers which are negative, well, I'll have to perform some more computations. So let's update the right hand side first. Right hand side get updated last. Oh, sorry. Didn't include the first row. I should have 3 constraints. So this gets updated to 3 over 5, a positive number. This gets updated to, what should I do to the second row? I should take the second row and subtract the last row divided by 5. So it's 1 minus 3 over 5, 8 over 5. What happens to the first row? I'll have to add 3 times the last row divided by 5. So 2 plus minus 3 times 3 gives. So it's 2 minus 9 over 5, 1 over 5. Okay, so this is something good. These numbers are all negative. These numbers, well, I don't really care about any of those except for which ones are basic variables. So which variables are basic? Of course, these ones. x1, x3, x4. it should get updated to 0, 0, 1. So how do I know that this is a x3 which stays basic and not x6?
Because we chose that one.
Yes, exactly. So x6 must have left the basis. x6 corresponds to the variable which leaves the basis. So the rows are actually about x1, x3, and x6. x6 left the basis. Okay, so now I have my new basis. Maybe it's also a good idea to find out what is the objective function. Also not very hard. I want to make this into 0. I'll subtract this row divided by 5. So it will be minus 14 minus 0.5. So it will be minus 13 and 2/5. So it's a good thing. The value of the objective function became smaller. So it gets some. I mean, we should solve several exercises like this yourself just to get used to what happens. That these numbers always stay negative, these numbers might or might not become positive, this objective function always decreases until all these numbers actually will become positive, or until you find out that your problem is actually not feasible. Solution to the new problem, or answer, x1 is equal to 1 over 5, x2 is equal to 0, x3 is equal to 8 over 5. These are my decision variables in the problem, and my new objective function is 13 degrees. Notice that it is very, very reasonable that my new objective function is smaller than the old one, because I have the same problem but with more constraints. Of course, the more constraints I have, the less freedom I have to find the less freedom I have to maximize my objective function. So once I add a new constraint, my objective function must become smaller. So it's only reasonable that from here to here it becomes smaller. So let me summarize this. Summary. If we add new constraints to the problem, the way to do it is like this. First of all, check whether the constraints are satisfied by the solution already found. So maybe some of the constraints are not actually binding. Maybe they are satisfied automatically by the solution which was already found. Okay. If yes, you are done. And then, if no, add the constraints to the final table. The previous final table. Well, this will destroy the basic columns in the final table. They will cease to be basic. Okay, they are not basic, but perform several row operations to make the basic variables basic in this table. So this step is about, well, you want these numbers to be zeros, except for these things, 1 and 1. Well, make them zero by performing several row operations. Well, it's always very easy because all other numbers in this column are zeros except for 1, 1. So you know which row operations you want to perform. Well, the new table is go feasible but not feasible. When I say dual feasible, I just mean the coefficients in the last row are all negative. The shadow prices are all positive, or the solution is optimal. Well, the new table is dual feasible but not feasible. Use the dual simplex algorithm. So the dual simplex algorithm keeps it dual feasible while making it at each step more and more feasible. So usually more and more of these numbers will become positive. So let me not start any new material now. Let me just make some comment about the midterm. So on the midterm, there will be, so first of all, we didn't finalize the midterm with the instructor, but as of now, it will consist of the following things. There will be one long problem about window output and interpreting it. So first of all, I did post a mock midterm on the website. So we'll try to solve the mock midterm. It should be somewhat similar to the actual midterm. So the actual midterm will consist of a problem about a linear program, its output, interpret, well, everything you can actually interpret from its output. Kind of dual shadow prices, reduced costs, some anything you constrain, whether it's satisfied or not satisfied, adding a new variable and seeing whether new line of production, whether it should be employed or not employed. So these kind of problems. That's just about duality. It's not about sensitivity analysis. It's just about small changes. Second problem will be about revised simplex algorithm. So what kind of problems could there be? Well, here's the original tableau, here's the final tableau, or maybe here's the basis, find the corresponding tableau, or here's the final tableau. In what range? I mean, how can you change, say, the right-hand side so that the new tableau is still feasible, still optimal? So these kinds of changes. But it will not include sensitivity analysis like we did here. So it will not include problems like here's a very large change in the problem. You update the table, it becomes not feasible or not optimal, re-optimize it. Such problems are not for the midterm, it will go towards the final. So the method will only include, once again, window program, interpretation of the output of window problem, which includes small changes, duality, shadow prices, reduced cost. So all these things you should know. Second thing, revise simplex algorithm. You should know the formulas how to go from one basis to another basis. You should be able to find out, say, in what range you can change a given coefficient so that the final table is still optimal. So that's all for the meeting. So next time is the meeting. And it will be once again for 1 hour. See you next time.